Hello, future engineers. Welcome to my YouTube channel. If you're still new to my YouTube channel, please don't forget to subscribe and press the notification bell so that you will be updated on my future videos. These videos are intended for engineering students, especially the civil engineering students. So this video discusses about friction problems, particularly about tipping and sliding case, application of the belt friction, wedges, and square threaded screws. So for the first problem, the center of mass of the 480 Newton table is point G. The table is supported by 4 casters, for which casters A are locked, and the friction between the unlocked casters B and the incline is negligible. The coefficient of friction between the locked casters A and the incline is 0.6. So determine the magnitude and sense of the horizontal force P for which the table is in a state of impending motion down the incline. So this is the figure, and take note that only casters A are locked and B are free to rotate. So let us compute the force P, assuming that the table will slide. Definitely it will slide downward because that's the condition here. The magnitude and sense of P for which the table is in a state of impending motion down the incline. So that's the given. So let's assume that the table will be at rest even without the application of P. Now, if P is applied and it will give us a negative value, it means that the table will slide even if P is 0. So if it is the case, then we have to reverse the direction of the force P so that it will hold or prevent the table from sliding down. So for the solution, so this P here is dissolved into 2 components, one parallel to the incline, the other is perpendicular to the incline. So the one that is parallel is P cosine 15 degrees, and the one that is perpendicular upward is P sine of 15 degrees. So we must remove the force P. Then the weight of the cable is acting at G, and we have normal reaction at A, friction which is up to the left because the given condition is the table will have impending motion down the incline. So 0.6 of NA, and at B it's only N sub B. Now, if this is the situation, there's no chance for the table to tip over B because there's no resistance along the incline. So tipping is not a possibility for the table about B. It's only about A supposedly. If it's only about A, if A would have been at a position of B. So in this case, no tipping will happen, and so we will only compute P based on summation forces along the tangential or parallel to the inclined plane. So we apply the weight 480 newtons. So we resolve it into 2 components, 480 cosine 15, and the other one parallel to the incline down is 480 sine of 15 degrees. So we remove also the weight 480 newton force because we have already resolved it into its components. So summation moment about B equals 0. So we have NA times 1.6, 0.8 plus 0.8, then plus 480 sine 15 times 1 plus P cosine 15 times 1.2, that's 1.2, So for 80 sine 15 degrees times 1 plus P cosine of 15 degrees times 1.2, then minus 480 cosine 15 degrees times 0.8 equals 0. So expressing NA in terms of P and constant, we have 154.18 minus 0.7244 of P. So since there's no chance for the table to tip about B because P is a ruler, there's no resistance horizontally. So we have to sum up forces along the inclined equals 0. So P cosine 15 degrees plus 480 sine of 15 degrees minus 0.6 of NA or equals 0.6 of NA. So minus 0.6 of NA, and NA is 154.18 minus 0.7244P. So let's substitute NA into this equation here. So for 80 sine 15 degrees minus 0.6 times the quantity 154.18 minus 0.7244 P, then solving for P or equals 0.6 of NA, this is NA, solving for P, P is negative 22.65 newtons. So it means that even if P is not acting, the table will slide down. So that's why P should be directed leftward. So let's have another situation. P is directed leftward. So these are the components of P, P cosine 15, and this time P sine of 15 is going down. And the weight and components of weight for 80 cosine 15 and for 80 sine 15, same direction. Friction is still in the same direction at A, 0.6 of NA up to the left. And we have normal. And at B, we have NB. So again, summation moment about B equals 0, clockwise positive NA times 1.6 plus 480 times sine of 15 times 1, then minus for P cosine 15 times 1.2 minus 480 cosine 15 times 0.8 equals 0. So expressing NA in terms of P and the constants, NA is 154.18 plus 0.7244. So it's almost the same as before, except that 0.7244P is now positive here. Then summation forces tangential. If tipping impends at A, it is now possible because A has resistance horizontally. So if that is the case, if tipping is about to occur at A, then there will be no reaction at B. So imagine that the caster at B is now not touching the incline. So that's why NB is 0. That's the only case where tipping is possible. So summation moment about A equals 0. So P cosine 15 counterclockwise positive times 1.2. Then minus P sine 15 times 1.6. Then minus 480 sine 15 times 1. That's clockwise. Minus 480 cosine 15 times 0.8. That one equals 0. So solving for P, P is 664.6 newtons, which is relatively high. So summation forces tangential equals 0 for 80 sine 15 degrees, then minus P cosine 15 degrees, 0.6 of NA or 0.6 of 154.18 plus 0.7244P, then minus P cosine of 15 degrees equals 0. So solving for P in this equation, it is only 22.65. It's the same answer as before, except that it is now leftward. So that's the value of P because it is lesser in value. So this P here will just be the amount of force that will prevent sliding of the table down the incline. but motion is still impending down the incline. So that's the answer to the first problem. So the second problem is about wedges. So determine the downward force F applied to the 160 Newton block required to move the 4,000 Newton block. The coefficient of static friction between all contact surfaces is 0.2. So this is the given figure. So first, let's draw the free body diagram of the 4,000 Newton block. So the effect of the force F and the 160 Newton wedge will be to push this 4,000 Newton block down to the left. So the reaction at the bottom of this 4,000 Newton block would be up to the right. So since the angle of friction is r tan of 11.31, so the reaction at the bottom of the block would be up to the right, making an angle of 11.31 degrees. So we will call the reaction as R1. Next, for F2 between this contact surface of the 4,000 and the wedge, we have down to the left. Let's call that FR2, and it makes an angle of 11.31 degrees with the horizontal again. So constructing the first triangle of this 4,000 Newton block, we have 4,000 Newton downward. Next is R1, which makes 11.31 degrees with the vertical. And finally, R2, which makes an angle of 90 plus 11.31 degrees, so 101.31 degrees with the vertical. And so the remaining angle is 180 degrees minus 101.31 degrees minus 11.31 degrees. That would be 67.38 degrees. So by sine law, we can solve R2. So R2 as to sine of 11.31 degrees is equal to 4,000 as to sine of 67.38 degrees. So solving for R sub 2 is 849.84 newtons. Next, we draw the free body diagram of the wedge. So we have the force downward F plus 160, and then we have to draw the normal of this inclined face. This normal makes an angle with a vertical of 75 degrees. So it makes an angle of 15 degrees with the horizontal, 90 minus 75, 15 degrees. And since the effect of this force will react this surface by up to the right, so therefore the resultant R3 will be making an angle of 11.31 degrees with this normal. So it is here. So this is R sub 2, 849.84, which is opposite to this, and the angle is 11.31 degrees. And R sub 3 would be here, and it makes 11.31 degrees also with the normal, and so it makes, the normal makes an angle of 15 degrees with horizontal. So R sub 3 makes an angle of 90 minus 15 minus 11.31 degrees with the vertical. And that angle is 63.69 degrees. So this is the first triangle of this wedge. We have F plus 160. Next is 849.84, which makes an angle with the horizontal of 11.31. So with the vertical, it makes an angle of 78.69. And so this is R sub 3, which makes an angle with a vertical of, as I said, 90 minus 15 minus 11.31 degrees, so 63.69 degrees. So this remaining angle is 180 minus 63.69 minus 78.69, so 37.62 degrees. By sine law, F plus 160 as to sine of 37.62 degrees equals 849.84 as to sine of 63.69 degrees. So F is equal to 849.84 times sine 37.62 divided by sine 63.69 degrees, then minus 160. Solving for F, F is 418.7 newtons. Example 3 is about square threaded screws. This problem was taken from the book by Ginsberg and Jenin, second edition of their book Statics and Dynamics, published in 1984. So the jack shown is The junction in cross-section consists of the threaded collar A, which bears on the frame B as it rides on screw C. The collar may be rotated by turning bar AB. The screw itself is prevented from rotating by the object being supported. The single square threaded has inner and outer radii 20 mm and 25 mm, and its pitch is 10 mm. The coefficient of friction for the screw threads is 0.4. The friction between collar A and the frame is negligible. Determine the smallest force applied perpendicular to the diagram at end B, D, or bar AD that will raise an object that applies a 5 kN axial force to the end of the screw. So this is the given figure, and imagine this is a lever, then we apply a force perpendicular to this plane of this diagram or this screen, and so the couple that will develop is equal to that force P times this moment arm 200 mm. And the formula is couple, or force times 200, is equal to W times the mean radius times tangent of the quantity angle of friction, P sub S, because we are going to raise the weight of 5 kilonewtons, so plus the lead angle, which is tangent of lead angle is equal to multiplicity of threads times P divided by 2 pi r, wherein the multiplicity of the threads is 1 in this case because it is specified single threaded screw. So C sub O is equal to WR tangent of P sub S plus lead angle. In this case, plus, because we're going to raise this 5 kilonewton force. If you're going to lower it, then we use minus P sub S minus theta. So P sub S is equal to R tan of 0.4, so it is 21.8 degrees. Tangent of lead angle is equal to MP over 2 pi r, where r is the average of 20 and 25, 22.5 mm, and m is 1 because we have single threaded screw. So tangent theta is 1 times 10 over 2 pi times 22.5. So the lead angle is 4.046 degrees. Then let's substitute it into this formula here. C sub O, which is P times 200, P should be in newtons. Then we express W in newtons also, which is 5,000 newtons times 22.5 mm, tangent of 21.8 degrees plus 4.046 degrees. So solving for P, which is the only unknown in newtons, so P is 272.5 newtons. So finally, we have problem 4. The 5 kilogram block A is at rest on the 30-degree incline with coefficient of static friction of 0.25. The coefficient of static friction between the cable and the fixed circular guide is 0.5. So determine the largest mass for block B for which the system is in static equilibrium. Since the question is about largest mass, so we have impending motion and the tension supporting the mass in B is the tight tension, and therefore the tension in this block A here would be the slack tension. Motion is impending downward for B. So let's apply the forces. So we have the weight, the components of weight would be 5 times 9.81 cosine of 30 degrees. That's the normal axis. So 5 times 9.81 cosine 30. This component along the plane down is 5 times 9.21 sine of 30 degrees. Normal at A therefore is equal to 5 times 9.81 cosine 30. This is the slack tension. P sub S, this is the normal. Since motion is impending up or impending down for B, friction should be down to the left, down the incline, 0.25 of normal. So to solve for NA, summation forces normal equals 0. So NA is 5 times 9.81 times cosine of 30. So this is the tight tension, which is equal to mass of block B times acceleration due to gravity. So for the angle of contact, let's analyze it. This is the slack tension. It makes an angle with the horizontal of 30 degrees. Therefore, the radius or the normal makes also an angle with the vertical of the same angle of inclination 30 degrees. Since this remaining angle, vertical and horizontal, is 90 degrees, then the angle of contact in degrees is 120 degrees. And we have to convert that to radians. So that's 2/3 of pi radians. So NA is equal to 5 times 9.1 cosine of 30. So NA is equal to 42.48 newtons. Then summation forces tangential equals 0 to solve for T sub S. T sub S is equal to 5 times 9.81 sine 30 plus 0.25 of 42.48. So the tight tension is 35.145 newtons. Then the relationship between tight tension and slack tension is tight tension is slack tension times e to the mu beta. Beta is 120 times pi over 180 degrees, so it is 2 pi over 3 radians. Then T tight is T slack e to the mu beta, mu s beta. Substitute mg, the T tight is mg, mb times g, 9.81, equals 35.145 e to the 0.5 of 2/3 pi. So solving for mb is equal to 10.21 kilograms. So I hope that you have followed the solution. And secondly, these problems are just basic problems on these specific topics. So see you on my next uploaded videos.